All right. Here's the test. It's just not going to be done on the same piece of paper. All right. I'm going to have you do this. One of the few tests I'm going to have you do on a separate piece of paper because it's mostly problems. There's no multiple choice, matching, short answer questions at all on this. That's the first time we've had a test like that all year. That's a good thing. It's a good thing because I'm going to give you partial credit. You will get a better grade, and you don't have to study. All right. Studying for these problems, after I'm done with the review, I don't really see it. I mean, it's nothing to memorize. It's all about having to, do those math problems, basically. So I can't imagine you'll do poorly on this test. And you get partial credit for getting, if you make a stupid math mistake or whatever, you get some credit. Let's go over, the test real quickly. The first 4 are oxidation number problems, like I have at the bottom of this. I'll do those at the end. Then there's about 10 or so naming or writing the formulas, like I have up there. Then, of course, there's a molar mass problem. There's a couple of conversion problems, converting in grams of moles or molecules or whatever. A percent composition problem, and 2 empirical formula problems. One where you're doing the empirical formula, one where you're doing the molecular formula. All right, it can't be a lot of these kind because they take up a lot of time, right? So there's only going to be 1 of these, and maybe 1 of these, or 2 of these, and 1 or 2, a couple of these, because they take up a lot of time. All right, there can be a lot of these. There are probably about 10 or so of those, and there's 4 of these at the bottom. That's it. That's the entire test. There are no surprises. If you can do what I'm about to go over right now, you can do well on this test. All right, let's start with these. First of all, if I gave you the formula I wanted the name, let's do this. I'm not going to write these down. I want to save a little bit of time. I don't want to waste too much time. K2SO3 is going to be, I hope you wrote, potassium sulfite, right? Now, if you want to look over here for a second, this will not be on the board tomorrow. You do not get the binary, ternary, and a little breakdown here. You have to know this, but it really isn't that hard because we've been doing it for about 2.5 weeks now. If it's just a metal and a nonmetal together, a binary compound, just the 2 elements and ide. 2 nonmetals, got to use a prefix, di, tri, tetra, whatever. If it's a ternary compound like K2SO3 is, it may be on the sheet. This guy was not. SO4 is on the sheet. This is SO3. 1 less, look over there. 1 less means ite, right? So this guy, that's why this guy was potassium sulfite. This one here, FeNO3. NO3 is on the sheet. So most people probably wrote down something like that's not right. Most probably wrote down iron nitrate. But they would lose a point for that. Only 1, but you would lose a point for writing iron nitrate for that. Why?
Because you didn't put the number.
Yeah, this is one of the transition elements. He has multiple oxidation numbers, and I have to identify them. Which iron is this? On your common ion sheet, there's iron 2, there's iron 3. Which iron is this? If you don't put that down, you're going to lose a point. Well, the nitrate's -1. So what must the iron's charge be? +1? No. No, because 2 times -1 is a -2. This guy must be a +2, so I put Roman numeral 2 there. Got it? All right. And the last one, or no, not the last one, this one here, N2O5, that is a binary compound, unlike these 2. So binary compounds, you're just going to end in ide. But because that's a nitrogen and an oxygen together, both of which are on the right side of the periodic table, both of which are nonmetals, I have to tell you, you have to tell me how many of them are there by a prefix. So I would have called this guy dinitrogen pentoxide. Would you have done that? I hope. All right, good. But I don't call CaCl2 calcium dichloride. I don't do that because calcium's a metal and chlorine's a nonmetal, so I just call it calcium chloride. Got it? All right, good. Now, writing the formulas, I'll do those for you. Mg +2, because he's in group 2, per bromate. Well, bromate on the sheet is BrO3 per BrO4. Has the same charge, though, -1. Hope you all wrote that, right? +2, -1. Good. Aluminum hypochromite. Al +3, he's in group 3. Hypoite, 2 less than the one on the sheet. Chromite on the sheet. Chromate on the sheet is CrO4, so he's CrO2. Got it? You need a 2 and a 3 there. Why? Because a +3 and a -2, there's no one number I can multiply it by. I have to find at least common multiple of 6. So 2 times 3 is 6, +6. 3 times -2 is a -6. The balanced charges always have to do that. They always have to equal 0. All right, nickel 2 hydroxide. Ni, I did this one for 2 reasons. Nickel 2, if I give you a Roman numeral, it tells you his charge. He's going to be one of those guys in the middle of the periodic table, the transition elements. Hydroxide is one of the few polyatomic ions doesn't end in 8. So you might be confused. See an I and think, oh, it's going to be binary, but he's not. A couple of them don't, and he's one of them. +2, -1, NiOH2, right? And finally, carbon tetrafluoride. Don't bother looking up the charges of carbon and fluorine. They'll never balance out because they're both going to be negative if you look up their common charges. Just look at what it says. Carbon tetrafluoride. That's it. If it said tri-nitrogen octa, you just look at it. You don't have to actually look the charges up. All you have to do is look up, read what it says, how many of them. And of course, the ones, I'll give you this little hint to you now before I leave him alone. Most of you know the common charges, di, tri, but the ones you don't, tetra, hepta are probably the two most common ones. So make sure you look those over, make sure you know those. All right, hepta would be what? 7, and tetra is 4. Okay. Pent, everybody would know pent, pentagon, pent, I would think. Hex, 6, so on. All right. Oct for 8, octopus. Okay. All right. Now, let's get to the harder problem. What's that? Nothing over 10. But it could be 9. 9 will be non. 10 is what? Deca, right. Okay. Okay.
I don't remember.
Now, let's do some Molar Mass problems. Believe it or not, Molar Mass pops up in multiple places. Here's one where I'm just asking you to get the Molar Mass. Then you'll need to get a Molar Mass to do a conversion. And you'll need to get a Molar Mass for a percent composition. So it shows up a bunch of places. So it's not like we only saw this one day. However, let's figure out a nice, easy one like this. I can't do him unless I know magnesium chloride's actual formula. So I write down Mg plus 2. Chloride is ClO3 with a -1. Got it? And therefore, it's correctly written. By the way, I will see people who will do this. They'll go through the trouble of looking up those charges, writing out the formulas correctly, and then not using them. Am I done?
Is it CL?
Oh, it's ClO2. I'm sorry. So chloride is one less. Sorry. Okay, back to my point though. This is the point to be made there. Me writing down a 3 by mistake. That's not the point. The point is this. +2 and -1. I've had people who will write every single one of those 10 problems we're going to have down there, write the charges out and not use them. Okay? You got +2, you got -1, you got to put a subscript of 2 down there, right? Okay. Now, let's go in. I need that in order to be able to do the actual chart for the Molar Mass, which is the element, number of atoms, times the atomic mass, giving you the total of that guy, and then you add them up. So for Mg, how many Mgs do I have? 1 times 24.305 grams gives you 24.305 grams. How many chlorines do I have? 2. Yo, look here. 2 is distributed across the parentheses, just like in a math problem. So I have 2 chlorines times 35.453 gives me 70.905 or 06. I mean, is that right? Yeah. And then finally, you've got how many O's?
4.
4 times 15.999 grams.
63.996.
Add them all up. What do you get for the molar mass?
159.207 grams.
Y'all get that?
Yeah.
All right. So that's how you do molar masses. And of course, molar mass pops its ugly head up all over the place. Look at the next problem. Next problem says, convert these guys, right? By the way, did I copy them correctly? Is that the right numbers? Their class, I screwed it up.
Yeah.
Is that right? 2.89 grams of CO? All right. So let's start 2.89 grams of CO. And I'm going to convert that to moles. So grams go on the bottom and moles go on the top like we've done since the metric conversions. What goes next to moles every single time? 1. And what's going to go next to grams every time? The atomic masses or the molar mass, depending on if it's a compound or an element. This guy's a compound, CO. So I add up carbon's mass, oxygen's mass. It's going to come out to be about 28 point something, right? Point what? Point what?
01.
01? All right. Do the math for that. What do you get? 103 moles, right? And that's a simple conversion. I don't have to convert. Look, there's like 6 or 9 different ways I can convert these guys. I gave you grams and asked for moles that time. Here I'm going to give you moles, 2.6 moles, and ask for molecules. Moles go on the bottom, molecules go on the top. 6.022 times 10 to the 23rd goes next to molecules every single time. We've seen that number from way back when. 1 goes next to moles every single time. I'm giving moles this time. All right. Do the math for that. What do you get?
1.6.
1 point what?
6.
1.6 times 10 to the 24th molecules. Is that right? What's that? You making fun of my handwriting? What's wrong with that? That's perfect.
I was sitting here thinking, like, what is that? 6.0
Nobody.
what?
Nobody. What is it? Now, this is a sad thing. Now, unfortunately, I think Ronnie's serious. She has no idea what that's.
I'm not. It's 6.022 times 10 to the 23rd. But when you wrote it, I was like, what is
Okay,
that?
so I'm going to ask you, what does that word say?
I'm going to say moles.
Okay, so it says moles.
No,
See, this is my point.
molecules.
It looks like
That's-
There, it just doesn't.
But this is my point. This is my point. You just made my point. All right. Obviously, we're writing it fast. It's the day of the review. The day I taught it, I didn't write it like that. But you have to know that it's kind of like saying, what I don't even have to say. When I tell you, somebody asks me, what's your weight? And I say, I'm 185. What do you think I'm talking about? Tons? Or am I talking about feet? I'm 185 feet tall? I mean, what do you think I'm talking about? Obviously, it's molecules. The same thing will go.
I kind of read my paper. It just seemed like confusing what he was writing.
It's not confusing. It's not confusing.
It's Monday
I
morning.
don't want to. Oh my god.
Hi,
Hi, Maddie. Maddie, I hope you're watching.
Emily's waving.
Yo, Emily's waving to you, Maddie. She's got a really bright orange shirt on. It's blinding me. But okay. It's not really that bright.
Sweater. I'm wearing a sweater.
Oh, sorry. Sweater.
I know, he told me, he's like, nice sweater.
Okay. 2.6 moles. Now this one, did I already do this one right? Yeah, I already did this one right. Okay, we did both of them, right? All right, we're done.
Lovely.
Okay, we did the conversions then. You're going to have a couple of those in the test. You did a molar mass, a couple of those. Actually, only one molar mass. And we're going to have this guy, the empirical formula one. Now, this guy here, we did a lab on. And I did, by the way, I did not give you guys. There was actually another sheet I could have given you. But there was, I think, at least 8 problems I gave you from the homework. How do we do this, guy? What are the ways we get confused by this one? I gave you this one for a hard problem because it gives you percentages instead of grams. Does that matter?
No.
No. Just pretend they're. Oops, there you go. Just pretend they're grams because you can assume any sample size. Assume 100%. 100 grams. So 22.1% of 100 grams is 22.1 grams of the liquid. I convert him, grams to bottom, moles to top. 1 mole contains 26.92. What do you get for that? 0.82, I believe? 0.82, 8 something?
0.819.
0.819. Okay, moles. All right, let's do the next one. 25.4 grams. Grams the bottom, moles the top. 1 mole contains, for phosphorus, he's 30.974. And what do you get for that? Also about 0.819 or 0.820 or something like that? 0.820, okay. And then finally I've got oxygen, so it's 52.5 grams. Grams the bottom, moles the top. 1 mole contains 15.999 equals, what do you get for that one? Isn't it 3 point something? 3.28?
Yeah.
3.28 moles. Now, that's your first step. You convert it to moles. Notice you see the same thing over and over again. You're seeing conversions from the beginning when I first taught them how to do it. But every time there's a little trick. In this case, the trick is, what do I have to do at this point? Divide by the smallest number, 0.819. Divide everybody by the smallest number, moles. Moles will cancel and leave you with 1 to 1.00 something, which basically is 1, to 4. Is that correct?
Yeah.
I can round up or down. And again, you would normally do it within this, but I'm going to tell you within a tenth. Okay? You can round up or down. What if, however, you got this? 1 to 1.5 to 4. What would you have to do then? I'd have to multiply everybody by 2 to turn this guy into a whole number. Right? So your answers would have been 2 to 3 to 8. But I didn't. It was actually 1 to 1 to 4. So my final answer is not 1 to 1 to 4. What is my final answer? ALPO4. Or ALPO. If you want to feed your dog. What?
Can you do the molecular formula from there?
What's that?
Can you do the molecular formula from there?
Oh, right. Good point. Good point, and for the people watching at home. I did not get a chance in your class to do this, and I should. That's the empirical formula, but the molecular formula could be any variation on that keeps the same ratio. So Al2P2O8 or Al3P3O. You see, you can do the same thing all the way up. In this case, if I would, in order to do that, I would have to give you the molar mass. The molar mass. I would have to say for example, this guy's molar mass is 150 grams. And I tell you that the actual molar mass is 300 grams. What's your real formula? Al2P2O. You see, you have to double everybody, okay? Now, granted, that would not be the case in this. AlPO4 is actually the empirical M. It's the correct formula for this guy. But I would do that on a problem that was a molecule that could do that in the future. And I will do that on the test. Guaranteed there's a molecular formula one on there, yeah. So you understand? Okay? So I will give you this, for example, I'll say that's the actual molar mass. That's what it really is. You will look up the guy you found as the empirical formula's molar mass, and you'll see if he's the same, you're done. If he's double or triple or whatever, you simply divide him into there and find out how many times he goes, and that's what you multiply by your subscripts. We did do these, okay? Now, you guys last week, you got to keep in mind, last week, you guys, I only saw one day this week, I'm going to see you twice every day, pretty much, except for tomorrow. I'm going to see you twice every day. So it's going to all work out in the end, and I know there was much rejoicing. Yeah.
I love this class.
Okay.
Period of Mr.
Yeah. Okay, look at now. Let's do the percent composition now. Again, what do I have to do to get? I didn't even have a chance. Listen up. I didn't have a chance to do this one at all with the other class, so I really want to be able to do this well. For aluminum pernitrate, I have to first write out the correct formula. You notice how all these things go back to, it builds on itself. Al's got a +3. Pernitrate is NO4 with a -1. So I have to do it correctly like that. If you didn't write out correctly, you can't get the rest of the problem right. You see? That's why naming and writing formulas is key. If you don't do this, you're going to get the rest of it wrong. All right. Now, a percent composition problem, once again, we're finding a molar mass. We've done it before. We have to find a molar mass for aluminum pernitrate. You know what I'm going to do. Number of element, number of atoms, atomic mass. Equals the total mass. So you're going to have aluminum, nitrogen, and oxygen, right? How many aluminums do I have? 1. How many nitrogens do I have? Hey, look. 3 nitrogens, right? And how many oxygens? 12. All right, now I'm not going to, but you should look up aluminum, do all these math. Well, I guess I will this time because I have the time and your class didn't see this. 26.982. Which is 26.982. 14.007, which would be what?
42.02.
021. And 15.999. What's that going to be?
191.98.
191.98. No, that's too many significant figures. So listen to this. This guy's got 1, 2, 3, 4, 5. Even though on your calculator you get 191.988, your answer is 191. Would be 1.1.99 then, if that's correct, right? 0.99. All right. Now add all those up. What'd you get?
260.
260. 260 what?
60.
Just 260. Oh, okay. Point what? 99. All right. And if that's correct, that is your molar mass. But you're not done. What do I now have to do to get the percentages of each guy? Well, for aluminum, nitrogen, and oxygen, I have to take this mass and divide it by the molar mass. That's part over the whole times 100 like I taught you a while ago. So for aluminum, it would be 26.982 grams over 260.99 grams times 100. For nitrogen, it would be 42.021 grams over 260.99 grams times 100. And for oxygen, it would be 191.99 over 260.99 times 100. What do I get for my 3 percentages? What'd you get, Bo?
10.338%.
All right. And next one?
16.1.
Well, that should have more significant figures than that. It's
Well,
got
it's a bunch of zeros after it.
0.100 then. Okay. And then what?
73.562.
All right. Now, if you did it right, that's your answer. What should happen to those 3 answers? They should add up to 100. Now, look, this guy may add up to exactly 100. It may add up to a little bit more, a little bit less. But they should be really, really close. Okay? And that's it. That's how you do the percent composition. You've done empirical formula, percent composition, molar mass. What's left? Let's see. Yeah, these guys. Now, I know those are the ones. Now, you notice a difference. And I guess this should be a lesson to you of why the thing that you probably hate the most about chemistry, besides me, is also the thing that is the most useful about chemistry. What I hate about chemistry, what you probably hate about chemistry is the fact that, gee, if I was absent, I missed this topic, it didn't go away. It's going to be there forever. It's going to build. It's also the thing that makes it easier. Because when you have an individual thing that you don't really see a whole lot, like I did these one day during this chapter, and then I didn't talk about them again. Now today, when I saw all you out there, I was like, well, I forget how to do these. Yeah, because you haven't been doing them every day. Whereas the naming stuff, you did every day. You couldn't do the molar mass unless you knew how to name it. You couldn't do the percent composition unless you knew how to name it. So you had to do it that way. These you didn't, so you don't remember them. That's my point. What do I want you to do in these guys? I want you to tell me the individual oxidation number of every element in there. Remember, I lied to you. Not all of those guys, even though we've been predicting their oxidation numbers to be a certain thing from the periodic table, all of these guys, besides oxygen and fluorine, can have multiple oxidation numbers. We wouldn't have predicted chlorine to be +5 or +3, but he can in the right circumstances. Okay, so of these guys that are in there, who do I know never changes? -2. Na and N, I have to make a choice. Look where N is and look where Na is. Who do you think is going to keep their common oxidation state in this case? Na. He's going to be +1. He's like the one you generally could tell by the ones that are furthest for the edges, because they're going to be more likely to lose or gain or keep their common state. So what does N have to be to make everybody equal to 0 at the end of this? Everybody see why it has to be +5?
No.
You should.
I do.
What's 3 times -2?
-6.
-6. What's Na? +1. And N is the unknown. So you see why N has to be a +5 in order for the whole thing to equal 0.
Yep, got it. Next one.
Now, the next one's really easy. Calcium has to be what charge?
Has to be 0.
I know most of you wrote +2. Calcium's by himself, people. What's his charge? 0. He has not lost or gained electrons.
So it's all uncombined elements.
So yeah, uncombined elements. And by the way, what's bromine's charge? Even if he's diatomic, what's his charge?
0.
0. And finally, I have the hardest one here, Cr2O7. Kind of have to do that one. Can't really do it in your head, maybe. Well, we just do it as an algebraic equation. If I know O is -2 and I'm looking for Cr, here's what you got. You got Cr2 -14 equals what? 0?
No.
Not for a polyatomic ion. It equals -2, the charge of the ion. So Cr2 -14 equals -2. So Cr2 equals 12. Everybody agree? What does each Cr have to be if 2 Cr equals 12? 6. Got it?
Those are tough.
Okay?
I'm not going to get those on the test. How many of them are there?
4. And they're easy.